Lecture number 11. Repetition, last time. Let's do 5 minutes repetition. Whenever I find it suitable, I do it. Otherwise, you have plenty of options of repeating things by going to the videos again. So anyway, let me still just repeat 5 minutes what we did in lecture 10, because this is really an important lecture for you in this course and for your future. This was the lecture where we were taught how to use the computer to do statistics or computations rather than theoretical probability. We should still use probabilistic thinking, and that is extremely important in many things out there that we want to deal with in the future. Things behave in a random way, and we need to be able to do computations on that if we are going to be engineers ruling our businesses, ruling the world in the future. We need to be able to compute things and learn from things and be intelligent about those random phenomena that are all around us, in the air, in the water, in our machines, in our cars, in our bodies, in everything. We have those random systems that we face all the time. And this course is one step towards being able, not to, because random is random, so we can never be certain, that's, but we can know about and try to think about the randomness and be intelligent about how we deal with it. That's what we are starting in this course. I'm not saying you're going to win the Nobel Prize after this course, but you have to make a first step, and this is one of the many first steps you are making during your study years here at our universities. Anyway, that was the big picture. Let's go down to the micro picture again here. We learned that we could do simulation as a tool to compute complicated features of random systems. That was lesson number 1. If I have a random system and I want to know something complicated which my theory cannot give me easily, like probabilities related to nonlinear functions of several random inputs, that is difficult to handle theoretically. That is easy with a few lines of simulation with the computer. Using well-known distributions, we can simulate and compute random complicated issues related to random systems. This was not really a statistics lesson. This was actually more like a basic computing probability lesson, the first part of it. Now, and then we started out to have a view towards statistics. We had sort of a sidestep that day, I admit, but it came in natural here for many reasons. This was the propagation of error. This is kind of the error thinking which is employed by many people in chemistry, in physics, in if I measure this and this and that and this and this and that and that and that, and I combine it, how do the errors sort of propagate through the system when I have some error inputs from the different things that I measure and I can do some computations? And what is the error at the final number? That was error propagation. We had some theoretical rules for that, but I also said that we could potentially again skip the theoretical rule and do simulation instead to find out how errors propagate through nonlinear systems. In fact, that was, in a way, more or less the idea of the first part, that you could do that. So that was just why it's relevant to take it up here. And then in a way, if you, depending on how you want to use the words, in a way, the propagation of error issue is at the core of what this whole course is about, if you want to use the words a bit more broadly than typically used. Anyway, the second part of last time was the statistics part. We learned that we could do confidence intervals by doing simulation, by having the computer resample our own sample again and again, sort of reuse our own data again and again to sort of emulate or simulate what kind of noise structure is there in our data. And it actually makes sense, even though it's called bootstrapping. It does make sense. There are more advanced versions of bootstrapping than the one that I'm teaching you in my note. So be aware of that. This is just an intro course. But the idea is valid. And the method that I give to you is also okay, but there are better methods for some situations. We learned how to do it in the classical 1 and 2 sample situations. That was to use the bootstrapping idea. That was the name of this simulation procedure where we have the computer resample again and again from our own data. We call it bootstrapping. We use it. We see how the average behaves from resample to resample, and then this distribution of how a computed average behaves from time to time. That is what we use for a sampling distribution rather than a theoretical result telling us that the sampling distribution is a t or a chi-square or whatever. We learned it for 1 and 2 sample situations. I told you it can be used for anything out there. Just yesterday I came back from a PhD. I was part of a committee evaluating a PhD at Copenhagen University, trying to show how you could develop bootstrapping methods for complicated process monitoring systems where you use multidimensional spectral data, chemical data, near-infrared reflectance data, for instance, at Lundbeck, to have very complicated ways of monitoring productions by high-dimensional spectral data, online measurements running all the time, and the way how could you set up statistical sort of monitoring ways. That's a classical engineering statistics discipline. We have a course on statistical process control you can take after this course. There are some basic methods, and then you want to employ that to multi-hyperspectral data, and you want to employ bootstrapping to have some reliable confidence limits for monitoring your processes when you do high quality and expensive production things as you do in, for instance, Lundbeck or Novo Nordisk or other places. Just to say you, the bootstrapping idea is something very important and also slightly modern, still being developed for some of the more advanced uses, more commonly used for standard uses. Okay. And then finally, I told you that there are other ways. We can also do hypothesis testing by computing raw computing force, either still by the bootstrap approach or by another approach, which was the permutation idea. There are other resampling ideas than the pure bootstrap. That was a short recap of what we taught last week. It is my experience by now that probably what I taught you last week is a challenge for many people in this course. But then again, challenges are not always bad, right? This is an important challenge for you, right? And I'm trying to give it to you anyway. Okay, that was a repetition of last time.